No in class today. No, the next couple in classes are a little bit weird because we're kind of doing like a back and forth with some of them are on mastering, some of them are not. So I just figured it's a little bit easier. For the one due from last lecture, later on today, and then Wednesdays will also be on mastering. So just for these couple ones, and then we'll have one for 17-2 once we get there. And actually, I can put that in now. The mess that it all is. All right, sitting here 12:10. We are in, I mean, if Friday was not the beginning of this, today certainly is. We are in the home stretch, team. You have made it this far into the course. Pat yourselves on the back because you've done a fantastic job of it so far. But we really are kind of on the train ride home at this point. We're getting there. We're getting real close at this point. And I think the last little bit of the course, the last 2 weeks will hopefully be, this is the last week that we've got maybe grindy work, if you want to call it something like that. But even then, some of our in-classes are more like FETs and things like that. The 2 weeks after that, we will still have some questions. There's still going to be some stuff going on. You're going to have a handful of things to do. I can't let you off the hook completely. But we get to talk about quantum stuff. And realistically, I'm not going to ask you to solve any specific wave equations or anything else like that. Nothing super crazy when we're actually talking about quantum stuff. It's going to be mostly conceptual, talking about a lot of the really cool things that we've got floating around in physics. So we get through this week and we're home free. That's what I'm trying to say here. Now, what stands in the way of all of this stuff? Well, first is something that you have already done, talking about exam 3 here. So let me kind of run through some of these details and everything else just to talk about some of these things. On Friday, I mentioned the average is completely useless, and I stand by that. I have looked through the data at this point. I have tried to plot everything out. I have cherry-picked my data exactly as I want to cherry-pick my data. Because let's talk about it like this. First, can we get... There we... Is that actually... Nope. Oh, jeez. Okay, hang on. First things first... Bunch of technical issues, and I don't think those are going away. Are they? Nope, they are not. Okay. We're going to restart this program. I'll just talk about these. I was going to draw that out while I was doing some of these things, but that's all right. So actual average, as you would see it on mastering, is somewhere around 40%, right? And I know that looks absolutely terrible, and when I first saw that, I was like, oh, geez. But... I'm not actually that worried about that number. I'm not super worried about that number. The reason that I'm not super worried about that number is because the distribution of grades for exam 3 is bonked completely. There is no reasonable comparison with the distribution of exam 3 to the other 2 exams so far. It just simply will not happen. There were, I think, among that average, some odd 40 grades in there that were contributing nothing. That's a combination of a lot of different things. Some people have multiple profiles. If there was an issue with your profile towards the beginning of the semester, then towards the second half here, you know, they had to do something to create a second profile. That first profile is showing up with a 0. There are people that have now dropped the course. Some of the TAs are on master, and all of those are factoring into a bunch of extra zeros that are bringing that average way down. On top of that, there were a lot of people that also skipped the exam. Or if you didn't skip the exam outright, then you perhaps took a glance over it and decided, nah, I'm happy with my first 2 grades, and kind of left it at that. So, what I mean by myself cherry picking the data, that the average and the distribution as a whole was simply not comparable to exams 1 and 2. In cherry picking the data, I have gone through, I have done a couple different metrics that I have chosen. I realized that my bias is in that, and I am not trying to present this as an objective kind of this is where the actual average is or anything else like that. But when I cherry picking a little bit of this data by saying, okay, so the extreme outliers, things that have changed in one way or another depending on your first 2 exam grades, if there was a missed exam somewhere, be that exam 2, exam 1, or exam 3, something of that might have shifted. There were a variety of things that I did to modify the data ever so slightly to, I think, give it a little bit more of a representative view of what the average had been had we not been dropping an exam, had everyone been full force on exam 3 as well. And when that average comes out, again, this is not an objective kind of value. It's much closer in the 60 to 65%, which is right around where I like to shoot for most of the time. Realistically, for a class like this, there's that distribution is where everyone sits. That is not an unreasonable kind of average for the course. That's actually a pretty solid average. So, all of that said, it is ever so slightly lower than I would have liked to see it, especially when you compare what happened with exam 2 and the curve that was associated with that. One thing that I do want to highlight while I'm kind of on this one, there have been a number of people that I have been individually looking through every single one of your sets of scores and everything else. To all of the people that had a really rough exam 2 and really turned it around for exam 3, pat yourselves on the back. I am quite proud of you. A remarkable turnaround on that one. I just wanted to give a little bit of recognition for all of those people that were like really grinding back out to claw their way back up. Congratulations. Well done. For the rest of the grades and everything else, and when I say the rest of the grades, I mean the grades as a whole, I will do a very, very, very slight curve for exam 3 just to bump it up a little bit more in line. Since I've already kind of broken my rule of not curving exams, we might as well take it all the way. A very, very, very slight curve, not by a very significant amount on exam 3, but just to set it around the same expected average as exam 2. But overall, I think looking at the data and everything else a little bit more closely now, I think I'm actually pretty happy with how that exam turned out. Somewhere in between the difficulty of exam 1 and exam 2, I think that worked out pretty well. I did try to make it not as clever and tricky as exam 2, and I think that succeeded, all things considered. Are there questions, comments, concerns about that? Anything that we're thinking of on that one? Anything that you want to ask about or anything like that? And you're also welcome, if you don't want to send it to me here, you're welcome to chat about it through email or anything else like that. But do we have anything right off the bat that I glossed over or didn't mention, or questions or anything else like that? Give it a few seconds in case somebody's typing. Hopefully not a super angry long message. Okay. So, let's talk about the next worst thing, right? I started off with hopefully trying to bring us into a cheery mood by putting in that we've only got 3 more weeks. But we do have one more thing, technically 4 if you want to think about it like that. We do have a final exam still, right? And the final exam is worth 25% of the course grade, so it's a little bit more impactful than any of the individual midterms. However, in talking about some of those details, the final exam is typically, and when I say typically, I mean going to continue going forward, usually somewhere between 60 and 70%, 50 and 70%, somewhere depending on how many questions there are and everything else, somewhere between 50 and 70% pulled from old material. It is a comprehensive final, which is something that I've been mentioning since the very beginning. Where am I pulling a lot of that old material from? The majority of those are going to be heavily inspired by old exam questions. So, it's a good reason to go back on those exam questions, take another look, figure out what was going on the first time. The questions will not be exactly the same. Keep that in mind, right? Because I expect that you will have written out solutions in front of you and everything else like that, because that's what we've got to deal with here. It's an online course. I know what's up. They will be slightly modified so that the original solution doesn't just plug into place, but these questions will be heavily inspired by old exam questions. So if you're starting to gear up right now, I would actually recommend, and I realize I'm asking a significant amount, but we are a 5 credit hour course, start looking at that material now, today, right? That way you can spend a week on each of the old exams, and that way you're coming into this with a little bit more preparation. You've got a little bit more time to mull over all the details. You can figure out everything that was going on the first time around. And then when we're getting towards the end here, when we're starting to focus much more on asking questions, reviewing, doing all those things, you are already prepared with the things that you know, the things that you don't know, the things that you need help with, all that good stuff. Right? So, please, don't wait till the last minute on this thing. I know it's at a pretty significant portion of the grade and everything else. And if you have been somewhere on the fence, this can be a fantastic opportunity to help turn that around, right? To really push yourself to one side or the other. So keep that in mind. And then the rest of that, the other 50 to 30%, whatever it would be for the rest of the exam, is going to be from our newer material. That is chapter 16 and onwards. So all of this stuff, still important. All the old stuff, still important. That shouldn't come as a surprise. We've been building up on our old material this entire time already. And the last detail on that one, I guess, probably the one you're most interested in, is because somehow I was taken off of the group schedule. Not sure how that happened, but we're rolling with the punches on that one. The final is going to be doing something like opening Monday at noon and closing Wednesday at like 4 p.m. or something. So it'll be a little bit over a 48-hour period, which is longer than a lot of these things, but that way it encompasses both sections, the time blocks that they would have had typically, and it also hopefully avoids what's going on with any sort of exam conflicts or anything else like that, right? You've got a pretty wide span there that you could find some time to get away from everything else to sit down for a little while. Will quantum mechanics be on the final? Yes. For our last exam was dropped, and this exam was the final is not included in the drop policy. Drop policy only applies to the midterms. Final is counted no matter what. How many questions will be on the final? To be determined. Same number-ish. Somewhere between 16 and 20. Not the final exam, 3. The lowest of all 3 is dropped. The lowest of all 3 of the midterms is dropped. So Canvas just sets that up as kind of a running, whichever is lowest at the moment in time is the one that gets dropped. Same amount of time on the final. Yeah, full 2 hours. Other questions, other things that we're thinking about right now? As we are gearing up for all of it. All right. Not seeing anything else at the moment. I'm going to switch this over before I... Oh, not that one. Before I forget what pen I've got. Let's go ahead and talk about the material for the day. We're getting into some of my absolute favorite material because I love to do optics stuff. So this is expanding waves, growing upon what we have talked about last time, right? So last time, let's think back to what we were actually talking about. We were talking about how do you send a wave down a string? What does that look like? Well, it's a wave going down a string, right? It's like a little hump and it just goes all the way down the string. And we have seen some different circumstances of that. If you've ever had a jump rope in your hand, I have to assume that at one point you whipped it and you would have watched that wave travel down. And this was the exact same thing. And I brought these up, but then I said, hey, what about what happens when I like drop a pebble into a puddle or a rock into a lake or anything else like that? You get these kinds of things. Water waves. Or if you've been in a wave pool, you've been hit by these on a much, much larger scale. But we generally recognize, hey, these are waves. We have used that in a popular kind of sense for, I think, a very long time without ever having taken a physics course or anything else like that. People know what waves are, right? It's just one of those popular kind of terms that we have for a lot of different things. But a lot of the times, we're not just focusing about these things on one single dimension. It's not just a string every time. In water, it's two-dimensional, right? It's a wave that travels over the surface of the water. So this is what I would call a wave in two dimensions, X and Y, or better yet, notice what this thing is doing, right? It's going out in a big circle. What's the easiest way to talk about a circle? Radial tangential, right? That's what I'm going to take to be the easiest thing here. And since all the way around the circle, it looks pretty symmetric to me, I'm going to argue the only part that actually matters is the radial part. That is, d of now r and t, instead of x and t, we just replace it with r, and then we have the exact same equation. Everything that we learned last time, surprise, surprise, applies in the exact same way. No changes. So, one of the things that is a little bit strange about this, though, is that as you go further and further and further out, think about what happens if you have ever done this. If you drop that rock in the puddle, what happens to those waves? If you do it in a lake, this is even better. If you've got a large body of water, maybe a large pond or something else like that, drop a rock in there. What happens to those waves? They go out and they go out and they go out, and as they go, they get smaller and smaller and smaller. Because now we're not just isolated along one dimension. You can almost think about this as like when you're shaking a string, all of your energy is going down a tube, essentially. It's not going anywhere else. If there's drag, there's some things like that, perhaps. But for the most part, all of that energy is going just along the line the entire time. It's not spreading out. But in 2D and in 3D, that energy is going to start to spread out. The amplitude might kind of remain the same, but everything's going to start to level out just a little bit more. And then by the time that you're across the ocean, or at the very least at the other edge of the pond, a lot of that energy has just dissipated down. It's out rather than being focused in one single direction. Which is where wave pools can get a lot of their energy, because they've got essentially a focus, right? That initial focus is not allowing that energy to change at all. It's got one single pathway that it sends out, and then that's why you're not supposed to go past a certain point a lot of the time, right? You're only allowed to go so far, because after that, they spread that out. The most intense waves are nearest where the wave is actually being generated, and then as it spreads out further and further and further, you get these smaller waves that are a little bit less intense for everyone. So, big takeaway here. For right now, we will talk about this intensity concept in just a little bit. But the big takeaway is that the equation that we were using last time is identical to the one that we're going to use here for 2D, and then by extension with 3D as well. But notice that our amplitude does ever so slightly change because it starts to spread out. So we'll talk about that factor in just a minute here. But for now, we need to kind of revisit phase. We might remember way back when we were doing this with springs. Let me go back to that equation. When we said, what's going on with a spring? Let's say a vertical spring. This is the equation that describes what was going on with its position. And we said this quantity right here inside of the cosine, the phase, phi, was equal to omega t plus phi naught. Right? However far we've gone in time, plus wherever we started, those two pieces. Now, the phase of what we're looking at now is, of course, going to be a little bit more complicated, but it's still essentially just what's going on with the oscillating term? What's going on with the part that's actually waving up and down, right? So now our phase term is going to include this k of x. Now it's a minus omega t, but for the most part, everything else is going to remain pretty much identical conceptually. The phase is where are we at in the wavy motion up and down. If we move to the right or to the left along the x-axis, then we're looking at a different spot, and how that's going to wave up and down is going to be a little bit different at that spot, right? And that's what the phase is going to be accounting for. time and space have an effect on where we are at in our oscillation. Now, we can do a comparison of a lot of these different points by looking at what their phase is doing. If we want to just look at the same continuous wave, then we could pick one x1, one x2, and we could take the phase difference between those 2 points. And if we do that, we end up with something that's kind of interesting here, right? Because what I could say is, all right, well, let me take the difference between these two, kx2 minus omega t plus phi naught, and we said, let's do this at the same time, at the same snapshot. And while we're doing these things, let me go ahead and move myself here before I end up blocking something that we need to see. But omega t, if we do this in a snapshot, if we do this at the exact same time, then the time cancels out. The phase constant, phi naught, cancels out. We're left with k, x2 minus x1, which k, the wave number, not spring constant wave number, remember it's a little bit different for what we're dealing with right now, is really just 2 pi over lambda. So we get these interesting kind of spots. These couple interesting spots that I'm talking about here, about if you are a full wavelength away. If I look here and here, the full wavelength away, they are exactly in phase. They will go up and down at exactly the same rate at exactly the same time. If I am only half a wavelength away, then what I'm looking at is a point like here and here, where they're going opposite. They're always doing opposing kind of motion. If they're both at 0, that's one thing, but it's going to be essentially one position is going to be the negative of the other one. So those are 2 special points, but I want to just kind of highlight those are special points. When the spacing between them is these specific values, either the full wavelength or half of the wavelength, we start to see these. Now, at the same time, we could also do what about between here and here? What is the phase difference between these 2 points that I've just highlighted? What do we think? Concept check on this one. Not 0. Along the same lines, but not 0. Highlight these one more time. Where's my draw? Not 3 pi, but 4 pi. Now, what's the difference between if I plug in 0 or 2 pi or 4 pi or 8 pi? If I plug any of those into a cosine, does cosine care? No. So this is arguably kind of a moot point, but it's still a relatively important one to have. It's kind of like when we're talking about that distance traveled, right? We're talking about, especially, it's not a big deal right now because we're dealing with sine waves. But if you ever have to deal with more complex waves, you're going to have to start to think about phases beyond just 2 pi. If you've got some crazy different types of wavelengths, you'll have to consider these to any sort of infinite phase difference that you might want to see on this one, right? What if I've got a really, really, really long wavelength and a really, really short one? Then a full 2 pi through the short one is going to be very different from the long one. I've got to consider a little bit more than 2 pi for the short one to actually make up some sort of meaningful difference between those 2 frequencies. But point of the matter is, for a spacing like this, my spacing is now 2 times lambda, 2 times the wavelength, and because of that, my phase difference is actually 4 pi. To have 0, we need to be lined up at the exact same spot. If I picked this point, and then I picked this point, same x, that's the only time we're actually going to get a phase difference of 0, because we are lined up exactly. Does that make sense? Are we on board with this so far? All right. So, but these 2, I don't want to necessarily focus in on one of them because both the wave number and the wavelength are both useful numbers to have. Either one of those can tell us the phase difference between 2 spots, assuming that we're looking at the exact same time. However, it's probably a little bit more practical to just think about this top equation. Because what if you're not looking at the same time? What if it's a different time? What if it's a different space? At any of those things that you might see, that's all right. You can deal with those things, right? And then just cancel out the things that are the same on both sides. If we're looking at the same spot but at different times, then the kx will cancel. If we're looking at, the same wave, but one of them starts just a little bit later, then maybe the phase constant's a little bit different. There's a number of different things you can have with these things. This top equation, I think, is the most useful. Take the phase as a whole. If you're looking for the phase difference, just subtract them, cancel out the things that actually are going to cancel out. To have three separate conditions, or, this is what happens when time is the same versus this is what happens when we're looking at the same space, it's nonsense. Don't cloud so many equations with one equation that's a little bit longer that handles everything for you. Let's try it out. A spherical wave with a wavelength of 2 meters. Spherical wave, what type of wave is that? 1D, 2D, 3D? Start there. Guesses? Not 2D. 3D is what we're looking for. And what's an example of a 3D wave? There's all sorts of different things this could be, right? We keep seeing 2D pictures, but because my hologram streaming is just not a thing yet, realistically. Think about shock waves from like a torpedo underwater. Think about sound as the sound wave moves out and you see the echoes. Those are examples of three-dimensional waves. They work exactly the same way as 2D waves, but they're now in 3D instead of in 2D. No difference besides that. So if I'm looking at this, it's a three-dimensional wave. The equation that we use will still be the exact same as we just saw for 2D, but at one instant of time, the phase at 4 meters is pi. So whatever time this is, call it 0 as a hint. That's what the phase looks like at that particular time, and that is the phase, not the phase constant, but the phase at the same time. What is the phase at these two other radii away from where it was emitted? Take the next 3 or 4 minutes to work on this one, and then we're going to come back together and see what you got. All right, let's go ahead and start taking a look here. So here is what I'm thinking. Let's ignore that stuff. That's not important for what we're doing right now. But, okay. Had to check to make sure it would actually work for more than a second here. Let's talk about the values that we're given first, right? We say, okay, in the given scenario, we know that the wavelength of this thing is 2 meters. That's a good start. And then I've got a weird one here. And how I'm going to write this out, I'm going to say, okay, at T1, they said at some time, whatever this would be, at T1, yes, I've absolutely forgot to do that. Thank you. Before that gets any further than it needs to be. At t is equal to 1, we've got a couple different things. Or let me just say at T1 is probably the better way to say this. At T1, we're going to call this the phase is equal to pi at R1 is equal to 4. So this is a little bit of a strange piece of information when we look at it like this, right? This is like trying to boil down some details, and I don't know if I would even normally write this down in a problem, but I do want to try and quantify to make sure that I know, hey, this is a particular detail that we've got. We've got one particular spot. We need to find, let's just call these values in a couple different things. Let's go ahead and say phase 2 at when R2 is equal to R4.5 meters. Let's say phase 3 at R3 is equal to 3.5 meters. And this way, it doesn't really matter what I've named these things. I could name them A, B, and C, or I could do whatever I wanted to. The main point of this is I'm just trying to quantify, hey, at one particular place, we had this. What about at this particular place? What about at this particular place? All of these places are different places that I want to focus in on, so I want to give them special names. Now, that means what we really need to do for any of these things, we know what the phase is like at one particular spot. And we also know now that we have a clever way of figuring out what is going to be that phase difference. So let's go ahead and say the change of phase is equal to, say, our final minus the initial. So I'm going to say phase of x minus phi 1. Now, x can be 2 or 3. It's the same equation in both cases. What is that going to look like? This is going to be something like this. K times x of whatever it is, whether that's R2 or let me do it like this. Let me not do x. Let me do R sub x. That way it's either R2 or R3. Minus omega, same time, so T1, plus whatever phase constant we had. Okay. Minus, same thing. But now, it's R1. Omega T1 plus whatever phase constant we've got. Omega T1 cancels out. Phase constant cancels out. A little bit easier this way. Now what we're landing with is K times R of x minus R1. This works pretty well for me so far. The last thing I'm going to do, just because I've got lambda, I don't have the wave number k, but I do know the k is just equal to 2 pi divided by lambda. That's the conversion between wave number and wavelength. So I can plug that in. And the only reason that I do this is not because I couldn't calculate k, it's just because I'm given lambda. I'm going to stick with lambda. It saves me from having to calculate out some decimals. So 2 pi divided by lambda, R of x minus R of 1. So let's go ahead and do this. Let me start with, I will do this one in blue. So for phi 2, phi 2 minus phi 1 should be equal 2 pi divided by lambda times R2 minus R1. Rearrange this a little bit. Say that phi 2 is equal 2 pi over lambda times R2 minus R1. R2, 4.5 minus 4. It's just really 0.5 plus phi 1. Plug in those last couple details that we need. I'm going to cancel out the pi and the point, or the 2 pi and the 0.5 is going to turn into just pi divided by 2 plus phi 1 is pi. My phase at this point, 3 pi over 2. And that saved me from having to do any nasty decimals, right? Because I've got a vendetta against decimals sometimes. Negative numbers and decimals. I'm just not a big fan of them. So that's what we end with. How does that feel so far? Knowing that we haven't solved the rest of this yet. I know I still have one more piece here, but I'm going to take now the exact same process. I'll walk through this, but it's going to be a little bit quicker. Highlight this one in green. Where did we get the 0.5? The 0.5 that we saw here, this is our 4.5. 4.5 minus 4 is what that is. So I'm going to do this again, but I'm going to do this now with phi 3. Phi 3 minus phi 1, same deal as before. 2 pi over lambda, nothing crazy going on here, times R3 minus R1. And in this case, we've got 3.5 and 4. So this is similarly, let me go ahead and just write this out. So let's do 2 pi divided by 2 is our wavelength here. Pi times negative 0.5. That is to say, phi 3 is equal to negative pi over 2 plus phi 1. Phi 3. Should do an arrow down there like that. Phi 3 is equal to just pi over 2. So why would we even care about finding the phase difference in the first place? Well, let me give you a little bit of a hint on some of these things. There's a lot to do with how waves smack into each other. When they have phase that is in phase, when they have phase that is out of phase. If you've ever tried this before, so this is a perfect thing, especially in newer cars. But in most any car, the position of all of the speakers is set up in a somewhat particular way. If you are sitting in your seat and you just move your body over a little bit, so you're leaning a little bit more towards the middle, the sound that you hear in the car will be a bit different. And the large reason for that is because your car is effectively a shaped cavity of some sort. The speakers are all placed in such a way so that when the waves are all bouncing into each other, you are getting a decent sound. That is, they have calculated out for a lot of these frequencies, what is the interference going to look like? How is the phase of all of these different sound waves going to line up? And when they line up and when they don't line up, changes how you hear your music. So they go for the best sound. They go for such a way that they make it that you're not going to hear this really weird beating out of phase or anything else like that. And that is one of the things that we will continue to talk about a little bit more. This right now, I know it kind of looks like where does this show up? This will show up in a couple different places, but it's easiest to talk about it right now. This becomes a lot more important when we start talking about wave interference, though. So just a little bit of foreshadowing on the stuff that we're going to see soon. But anyways, talking about things like that, you might have already guessed, sound waves are a fantastic example of some of these 3D waves. Right? I am not talking directly into a line. In fact, my microphone's about right here. I am a little bit above it. It's a little bit to the left of me. So my sound waves, as they go out into the rest of the room, they bounce off the walls, they do a bunch of other things like that. It is a three-dimensional wave that actually reaches my microphone, though. And then if we even want to go so far to talk about that difference, we're not going to talk, well, let me wait for intensity just a little bit longer. Let me do that example in just a little bit here. But sound waves are a little bit interesting because they're not visual in the same way that a water wave is. We can see the waves on the surface of the water, right? That is a very easy to visualize thing. There is a flat plane of water and the wave moves as some hump over that flat plane. Sound waves are a little bit different because what's really going on here is it's compressions and refractions of the actual gas molecules itself. So in some spots, a lot of them get clumped up and that clump kind of propagates forward, and that's how the wave moves in 3D. It's a little bit strange, but that's all right. It's what we would consider a longitudinal compression because that compression is going in the direction that it's traveling, right? That compression is essentially traveling forward, and when that compression and rarefaction hits you, that's what you actually hear as sound. Because sound is a very common wave that we will see quite frequently here, we like to focus on it just a little bit, right? It is one of the big waves that is kind of all around us constantly. This changes on a day-to-day basis, but go ahead and say the speed of sound is right around 343 meters per second, called Mach 1, if you want to go for something like that. It does change on a day-to-day basis, though. Technically, it depends on things like humidity and temperature, and there's a lot of different things that can start to affect what that speed of sound is. But on average, 343, I think that's a fair value to use. For all of these different frequencies, this is essentially how rapidly do these things compress? How rapid are these compression cycles that go through? Wiggly air. The lowest we can hear is around 20 hertz. And this is not actually something that is... This is not even... this is a little bit of a strange thing. This gets into physiology more than anything else, is what I'm trying to say. Because what happens when something is slower than 20 hertz? Does anyone know how do we hear sounds that are less frequent than 20 hertz? Any guesses? What about something, let me try something like this. It's not even that we feel them. We still hear them. Let me show you a 1 hertz sound. That is 1 hertz. Hertz, I don't know. What's a singular hertz? I don't know. we hear it not as a sound anymore, but actually as a rhythm. So that's one of those strange things that's a physiology thing more than anything else. The physiology is very much about how do we hear these sounds. The 20 hertz is right around kind of the break point for how you hear that sound. Is it a frequency or is it a pulse? So it's not really necessarily a physical thing. It's just how our brain interprets that sound. Above 20,000 hertz, though, it's too fast for our ears to actually pick up in a reasonable way. It's just too high. Some people can hear a little bit higher than that. Some dogs can hear higher than that. But generally speaking, 20,000 hertz is about where it starts to peak out. And then as you get older, that will actually go down a little bit more as those, that very, very fine listening starts to degrade in your ears. So, let's try this on a problem. Let's imagine something here. Assuming the typical human voice is at a frequency of about 500 hertz, and that might be a little bit high. I don't know. There's a combination of frequencies. Anyways, what is the frequency of the human voice after you breathe in helium? And you probably know this effect already. When you breathe in helium and your voice shifts up by like a full octave, it goes really, really high. Here's where that comes from. Try this. Find what frequency would that be. Take the next couple minutes and see what you get. Okay, let's try this one though. So the equation that we're looking at for this one is not one of the ones that we talked about, right? We're kind of drawing on that old information, but it's not a complicated thing, I promise on this one. Here's what we need to think about. The equation that I'm considering is that there is a velocity for any traveling wave, and for many of these, it depends on the medium, of course, but that expression for the speed of the wave, it depends on two things. Or rather, this relationship between the frequency and the wavelength tells you about the speed of the wave. So when we're looking at something like this, I would say, okay, well, my frequency is 500 hertz. Now, here's a bit of a strange piece. What happens when this is going through helium instead? So what changes? Let's say you breathe in a bunch of helium. What has changed? What actually produces the sound? When we're speaking, when I'm speaking just like this, what's actually producing the sound? How do I determine where that pitch comes from in the first place? What do we think? Not the part where you're hearing. I'm talking about the part that I'm generating. If I was screaming and nobody was around, I would still be screaming. I would still be producing sound. I know it's a philosophical question, but I promise physically, I still scream even when nobody's around. But what's actually causing that? The vocal cords. They're a physical structure. The sound of my voice naturally is going to be essentially coming from the natural shape of my vocal cords. When I breathe in a bunch of helium, not that I have actually, but if I were to breathe in a bunch of helium, that structure does not change. The wavelength, if the wavelength is generated by what's actually going on, imagine it's a set of strings. It's a muscular, strange set of strings. The wavelength of those strings, or the wavelengths of those strings, does not change. So this is a really unique circumstance because that means the wavelength is a constant here. The wavelength is not actually a changing quantity, but the frequency because of that might be changing. So when we look at it like that, let's first rearrange this thing. Let's go ahead and solve out. So let's say this is the frequency in air, F sub A. When we do that, now what we end up with here is that lambda is equal to the velocity divided by the frequency, and we get a wavelength of something like 0.686 meters. So a pretty long wavelength if you really think about it like that. But let me take that quantity. Now I say, okay, well, this is something to do with the vocal cords. And the vocal cords, despite the fact that I breathe in helium, do not change. They're part of the physical body. They are not going anywhere anytime soon. So now we shift that. Now we say, okay, take this into a new circumstance. This wavelength holds constant. What happens when we change the velocity? Same thing as before, but now I'm solving out for frequency, and I'm going to say frequency in helium is equal to the velocity in helium, and let's go ahead and sub A, right, for air. Now for helium, divided by the same wavelength, because it's the same thing generating the sound wave, we plug in all of those quantities, and we get something like 1414 hertz, which, if you know anything about music, that's almost 2 octaves up from the original sound. So that's why it sounds like it goes super high, because it's nearly 2 octaves up from the original sound. The wavelength is constant because sharp G natural, you perfect pitch people. The value that I plugged in for V sub A, that is our speed in air, 343. Oh, and we're going to specify what tuning we use for A. Come on here. But anyways, what we're doing with this, the wavelength is a constant because what's actually generating this? It's essentially some sort of, call it a flap, more or less, is what your vocal cord is, right? Vocal cords. It is more or less going to be some piece that vibrates at a certain frequency / wavelength. But realistically, what it is, more than anything else, when I talk about the frequency that it's going to be oscillating at here, what it's doing is it's trying to essentially create this wave in the first place. As it tries to create this wave in the first place, it is going to be going back and forth something like this. It is going to be setting the wavelength of this wave regardless of what the air would be there. If you tried to scream in space or anything else like that, and I know that's going to be a very dark thing. If you tried to scream in space, though, your vocal cords would still vibrate to try and generate that same wavelength as before. But it wouldn't be able to do so because there wouldn't be anything to send it through in the same wave, but it would still try to vibrate and send out the waves at the same wavelength. The frequency is in part determined by the air that's already in there. So your body is what's going to be giving some sort of pulse to this in the first place. It's trying to generate the wavelength. The helium that is passing through it instead is allowing that wavelength to move at a much faster frequency. And that's why the frequency is changing, but the wavelength does not. The wavelength is determined by the structure generating the sound in the first place. Don't even get me started on the differences of tuning either. That's don't even get me started on that. Benefit is I'm a classical guitar player, so I don't have to tune to anybody. I can tune to my own instrument and anybody else can deal with it. But non-standard tunings drive me insane. Does that make a little bit more sense, though, as far as it goes for it's the structure that's creating the wavelength in the first place is still there, whether or not helium or nitrogen or what's the sulfur hexafluoride? Is that the one that they use for super deep? I think that's the one. Side note, don't do this a lot. As a general safety warning while we're talking about these things, helium is relatively fine to do. I know a lot of people have done this and everything else, and it's for the most part very safe. Don't do it for a long period of time because you will literally drown and drown on dry land. So don't be doing this because when you are sucking up a bunch of helium, that's displacing the regular air that you need to breathe. The difference is that helium is the lightest gas. I mean, technically hydrogen gas, but hydrogen gas is a little bit of a different thing. Helium is the one that will go anywhere. It just you can't hold helium down. It flies away. It's completely inert with everything else. So if you take a few deep breaths, you'll mix all of that helium back out of your lungs and you'll be totally fine. Sulfur hexafluoride, whatever it's supposed to be, chemistry things, that's a super, super heavy gas, and it has the exact opposite effect of lowering your voice by another octave or two. The problem with that one is that it is a much, much, much heavier gas, and that will sit in the bottom of your lungs, and that is a very large hazard. Do not do that, as a warning for everyone on that. I know it's one of those fun things to experiment with and everything else, but if you and your friends are playing around with a bunch of sulfur hexafluoride, be like, hey, be careful with that. Do it once, and then take a lot of deep breaths, really deep breaths to blow all the air out, and a lot of deep breaths to try and displace that a little bit more. Or quite literally hang upside down, because it's heavy. It will fall down to the ground. Anyways, that's my safety disclosure while we're talking about some of these things. But, and I've even got kind of a note down here at the bottom if you want to get into it. The whole thing is, this is a very poor kind of assumption. Also, absolutely don't do band. Your GPA will plummet. As somebody who is quite experienced in band, your GPA will absolutely plummet. Anyways, let's try something a little bit different here. And this is a really fun one. I've got a video to go along with this. It's a fun little channel, but this is like a 10 or 15 minute video that does a really cool thing of showing a lot more of this physiology. Why do we have our ears in the positions that we do? They are offset in certain ways. If anybody has ever noticed that, your ears are ever so slightly offset. If you wear glasses, you are certainly aware of that. Because your glasses have to be a little bit tilted one way or the other to account for the fact that your ears are at different heights. All of that is about helping our spatial awareness as it goes with sound. So let's imagine a scenario here. What kind of times, when we're talking about sound moving around and how's our brain trying to interpret spatially what sounds we hear, how do we actually do something like that? Let's imagine something like this. Your ears spaced, say, 20 centimeters apart. Let's consider a sound source 5 meters away from right in the middle, but it's out 45 degrees to your right. So directly in front of you, 45 degrees away from that, 5 meters away, a sound source. What is the difference in arrival times between each of your ears? What is that difference in time? How long it takes to get from one, and then the difference, how much longer does it take to get to the other? Calculate this one out. I'll give you a few minutes to do this, say 3 or 4, and then we're going to take a look at this together. Okay, let's take a look at this one. So first things first, we need to figure out some sort of way to actually model this, and that's going to be probably the trickiest part of this entire thing. Because the rest of this, if we can figure out that, it's just kinematics. So let's take a look at what that's actually going to look like. Let's draw this thing out, of course, because drawing is our favorite thing to do in physics. Let's have this. Let's imagine, let's even do this. The human head. Look at that. Beautiful. Right? Something like that. And then we have 1 ear, 2 ears. Wonderful. All right. We said from the center of the head, I'm going to draw a little tiny X right there. From the center of the head, 5 meters away, 45 degrees away. So let's draw, there's our vertical line. Here is supposed to be 45. 5 meters away. I know what kind of a disaster this looks like, but that's all right. We're having fun here. You don't need to draw good pictures. Or let me say it like this. You don't need to be good at drawing to draw good pictures in physics. 45 degrees away from center. So if our head, 20 centimeters ear to ear, then what I've got right here is a 10 centimeter distance, or let's say 0.1 meter, 0.1 meters. Now, you might be looking at this, and you might be saying, hey, wait a minute. I know what you're doing. You're trying to draw triangles. And I would agree with you. Yes, I am. That's always my trick. Every single time, all I'm trying to do is draw a bunch of triangles. So let's go ahead and do something like this, something like this. Let's make what should be a right triangle. That's all right. A little bit of a disaster here. That's what we love to see. A right triangle just like that. Now what I'm going to draw here is I'm going to set up both of these things to have one red path, one blue path. Those are my two distances, as I need them to be. So what I need is I'm looking for essentially my blue path, the R for this one, call it R sub B. I've got R sub A. And then right in the middle here, I'm going to call this R sub C for radius to the center. So we have some sort of, how do we draw this? Speaker looks kind of like that. Sound. There we go. Something just like that, right? Again, fantastic pictures. We need to find R sub A. We need to find R sub B. We know what R sub C is to begin with. So what is my trick going to be? I also know that this angle right here is 45. What I'm going to do is I'm going to start by finding, let's see, which distance is probably the best one to do here. Probably this bottom distance right here. Since it's some sort of bottom distance, I'm just going to call this D for now. Random variable names as we need them, right? My favorite thing to do. So if we go for something like this, I would say, okay, well, I know, given a couple different things here. Let's write these out before I forget any longer. Velocity of sound, 343 meters per second. R sub C, 5 meters. And then the angle, 45, we've already got drawn in the picture. So if I'm trying to solve out for D, here's what I'm going to try and do, right? I'm looking at, I should have drawn a little bit more of this in the other colors, but that's all right. I'm looking at for just this black line in the middle. Black line in the middle, black line on the outside. I've got a right triangle that looks, let me draw it out to the side with a line, please. Hopefully this makes this a little bit more clear. 45 degrees, D, R sub C. That's what I'm looking for. Because once I have D, the reason I'm solving for D rather than this side over here, this side over on the right side is, of course, shared between everything. That would perhaps be a useful value to have. But the problem with it is I don't know how that changes. How do I use that side to figure out what's going on with the R of A and R of B? If I find R of C first, then I know if I essentially increase it by 0.1 meters, I have my ear on the left. If I decrease it by 0.1 meters, I have the ear on the right. So we find D first, and then we've got that bottom side of each of our triangles. We could use that to find the hypotenuse. Actually, it'd probably be good to have both sides. But because this is one of these, 45 and 45, I forget what, I'm failing geometry really badly right now. Those same sides, 45 degrees, 45 degrees, D should be the same on both sides. Whichever of the three flavors of triangles this one is, those two sides should be exactly the same. So let's find D. Let's stop talking about it. Let's actually do this thing. R of C times either sine or cosine would work perfectly fine. Times sine of 45 degrees. And yes, you can just immediately go to a square root of 2 with this thing. And I think other way around. D, or yeah, that's right. Never mind. Sorry, I'm responding to the comment in here. Yes, that's what we should see. Something else like that. What we end up finding is that this quantity right here is equal to D is equal to 3.54 meters. So that bottom side is 3.54 meters. This side right here is 3.54 meters. The last thing that I'm going to do here to make this just a little bit easier, right? So now I've got each of these sides. What I'm going to say for the right side, I now have a triangle where one side is 3.54. Let's draw it out like this. I don't know what these angles are necessarily, and that's all right. What I do know, R sub A, 3.54 on this side, 3.44 on this side. Between those two, Pythagorean's theorem, right? Plugging in those quantities right there, R of A should give us something like 4.92, and let me even go with all the decimals. I'm just going to write this one out. 4. Let's make it look like a 4. 929 796. And I'm going with all the decimals on this one because they are going to be pretty important. Quantity to start. Now, we do the exact same thing with the blue side. We say, all right, now I'm looking at the left here. Now, the base of my triangle, and I'm exaggerating all of these distances. What I should have at this point is 3.54 on this side, 3.64 on this side. So R sub B, Pythagorean's theorem again, should give us something 5.071, 204. Some really extreme decimals. Just trying to keep track of all these details. Now each of these covered by speed of sound, distance divided by velocity gives us a time. So the time it takes to reach the left ear, the distance divided by the velocity, is going to give us something like 0.0147. 849. In seconds, to reach the right ear, it's going to be something like 0.0143726 seconds. Finally, our final answer is the difference between these two. Delta T is equal, and let's go ahead and even just do it like this. TB minus TA, just so we're explicit, all the way through. Something like 412.3 microseconds. How fast is a microsecond? Well, this is about 1/2 of a millisecond, which was already 1,000th of a second. So this is pretty quick. This is pretty instantaneous, all things considered. But this difference is enough. The human brain, and not even just the human brain, many animal brains are able to perceive these kinds of time differences, not necessarily consciously, but a little bit more of a subconscious. We're able to process these slight delays between what are two ears here to immediately be able to identify where objects are at. And again, I highly, highly, highly do recommend, if you want to just watch the full video, you can just watch the full thing down here at the bottom. Right now, I would recommend, if you want to just get to the part that's a little bit more important, around 3:15 is where this starts. But it is a really cool video demonstrating this for people that, essentially being able to identify where different objects are at, how our brain takes care of all of that information, and what you can actually do to kind of screw it up sometimes. So, mostly geometry. More than anything else, a lot of geometry, not actually very much physics to it. So, let's talk about my favorite traveling wave, light. I love this one, right? Because, of course, I'm very involved in optics. Optics is one of my particular interests. And we will end up talking about this a little bit more later on, about where some of these values come from. But light is, if not something that we realize, arguably the most common traveling wave because it's everywhere. It is everywhere. And I mean that quite literally. There are constantly waves, electromagnetic waves traveling through you. The light that we call visible light, what you would popularly say is light, is really only a portion of a much larger spectrum. And on that spectrum are all sorts of other different things. X-rays, gamma rays coming from deep space, microwaves like used to heat your food is also in the light spectrum. Infrared, if you want to talk about thermal vision or anything else like that, that's coming from infrared. If you're talking about radio stations that you like, or if you still get satellite TV of any sort, that's coming from AM and FM radio. If you're working off of satellite internet or anything else like that, That's where a lot of this comes from. The software update sent to the helicopter that's on Mars right now was done so using radio, light, once again. And all of these are essentially the same variety, but different wavelengths and different frequencies of light. People still listen to radio, allegedly. I don't know that anyone still actually does, but I'm told that it's still a thing that exists. But there's a couple strange things about light. Light's a little bit more unique, and it's not one that we're going to be able to get to in super high detail quite right now. But suffice to say, there was a lot of debate over what light was for a very, very, very long period of time. I have brought this up before. We have waves. We see waves. We might have even seen this sometime before where we talk about, okay, what's an electric and a magnetic wave, and these two waves do something to cause it to send forward, and you're like, sure, whatever. I don't have enough information to really refute that. I'll take that at face value, and thank you. I appreciate it. Makes my life a little bit easier. But you also might know that it can act as a photon, as a particle, and both of those descriptions are true. But that gets into kind of like our matter waves description of like, stuff's a little bit funky sometimes. But more or less, all of these things can be created by oscillating electric charges. So if the charge moves up and down like a spring would, it creates an electric wave, it creates light, just like any of these other traveling waves, but it doesn't require a medium. And that was a really strange point. And it was actually here in Ohio that we did an experiment that proved that there is no spatial aether or ether or ether or whatever you want to call it, however you pronounce it, that is permeating through space. There is no medium for something like light. Light is allowed to just travel through empty space. No magic space dust. That was what the experiment showed. So, but light also has this particular thing where in a vacuum, it moves at a finite speed, 3 × 10⁸ meters per second. It is the speed limit of the universe. Nothing can move faster than the speed of light. So, where do we see some of this stuff? What is our most common light? Well, probably the sun, as far as I'm concerned. There's radio waves and all sorts of different things buzzing around, but if I want to talk about light that I am like definitively aware of, nobody can deny for the last few thousand years, it's going to be light coming from the sun. And there's a few different ways that we can talk about things like light and waves, right? We have seen power before. That is not anything new. That is the rate of energy. Energy divided by time gives us power, but intensity might be a little bit more new. Intensity is power per area. Why do your headlights not work for something 20 miles away from you? Well, because the light spreads out. Why do I sound different from right here versus really up close to the microphone? It's because as the wave travels out, the amount of energy, the intensity, changes. Between all of those different values, we can see this change of intensity, and that's why there are certain times when we're looking at things that are safe for their intensity, safe from a certain location, things that are safe from a different location. Lasers, actually, are classed partially on how much they diverge. Because a diverging laser is less dangerous than a coherent focused laser because the light goes out. Less intensity, less power per area. So if we're looking at any of these values from the span of a 2-dimensional wave or a 3-dimensional wave, 2-dimensional, let's focus on to begin with. This is probably the easier one. And I'm not doing an ASMR physics. Maybe after I'm unemployed and I've a lot of free time on my hand, I'll consider it then. But not until then. I use my teaching voice instead, and my teaching voice cannot be super close. If you've ever talked to me in real life, I don't talk this excited all the time. I've got sad news for you all on that one. This is my teaching voice, my teaching persona. But for any of these things that we would see, what we're basically doing, if the wave is being generated right here, and let's say this is a water wave, then, or actually, just kidding, this is a spherical wave. This is in uniform 3D. This is the surface area of a sphere. The intensity spreads out. The larger you are from the source, the less intensity that you have. And this is going to be a little bit of a strange one. So most of these things are going to be measured in watts per square meter, which is literally power divided by square meters, surface area. right? But for sound, we've got a slightly more strange unit. We've got a sound intensity unit measured in decibels. And that's kind of disingenuous in its own right because decibels itself is not actually a unit. It's a kind of a unit, but it's like a logarithmic unit and it's not specific to sound. Sound is messy. I don't have a good answer for that one. Really, what a lot of it is the fact that our ears are so incredibly sensitive that they can hear low intensity, high intensity sound is about 1,000,000 times difference. A whisper is extremely quiet versus something that's very loud, and our ear can perceive all of those things. And that means that a linear scale doesn't work super well. Yeah, our ears are wonky. They're real wonky. If you want to get into that stuff, that's a lot of really cool things go into our hearing. So for hearing and sound in particular, we've got like certain set values, and then we've got this strange scale going down on here. But generally speaking, this equation that we see in blue here, that's the main anywhere that you go, intensity comes from this equation. The units that you report those in, for sound specifically, is a little bit different, but the intensity is the same no matter what. So let's try this. Solar luminosity is about 4 times 10 to the 26th watts. So that is how much power the sun is putting out. 4 times 10 to the 26th joules every single second, which is a lot of energy. What is the intensity of this solar radiation as it reaches the Earth's atmosphere? So that is to say, okay, so the sun radiates all this power out, and then it goes out in a big spherical wave. By the time it reaches Earth, what is the intensity? Second, if the cost of energy, and this is a little bit high versus Oxford, but some areas are a little bit different. Let's say it is 10 cents per kilowatt hour. That's what that unit is trying to say. Think about what that means. Kilowatt hour. It is a unit of energy. How much money does the sun throw at Earth every single day? I want you to take the next 5 or 6 minutes to work on this one. And you have to think about how much energy is the Earth actually able to pick away from the sun, because it is not collecting all of the energy. Got bad news for all you sci-fi fans. We are not collecting all the energy from the sun. Most of that energy is just going off. We've only got a little tiny portion of that we actually collect. And when I say little tiny portion, I mean thousands of square miles. So 5 or 6 minutes, work on this one a little bit, then we'll come back together and see what you got. All right, let's go ahead and start taking a look here. So we really only have, well, a handful of values here. And to say a handful, I mean 2. And really only 1 if we're focusing on here, part A. So we need some extra details. Some extra details that are not shown in this slide. What are those extra details that we actually are going to continue to need here? Any guesses? Hopefully from people that have tried to solve this problem out and realize what values we actually continue to need. Whoops, for times 10 to the 26th watts. Distance from the sun, that is certainly a pretty big one, at least to start. Right, so let's go with that. Let's say R, and I'm going to call this R sub D, R distance from the sun, some sort of quantity like that. And I'm just going to take average value, whatever that's going to be, right? It doesn't need to be any particular time or anything else like that. So if I'm looking for that quantity right here, that should be something like 1.5 times 10 to the 11th meters. Yeah, I don't. Where we're at with solar power of humanity and everything else, we've got a ways to go quite yet. So if we're looking for the intensity, and we're basically saying, okay, well, the first thing we need is find intensity. Intensity, power per square meter. Power divided by, this is going out as a spherical wave. So think about what that means. A spherical wave, what is the intensity look like here versus here versus here versus here? What's going on because it's constantly emanating out. That's why I'm dividing by the surface area of a sphere. This same amount of power is expanding out. It's blowing up like a balloon. But as it blows up like a balloon, think about what happens when you blow up a balloon. It starts as a very solid, you can't see through it at all. It becomes a little bit more transparent as it blows up and up and up and up and up till you can start to see inside of it, because the same amount of material, the same power, is stretching out over a larger surface area. So we plug this in. We say, okay, well, the distance from the sun, r sub d squared, we've already given the power, we've already got that radius right there. We plug in all of these values and we get an intensity, something like 1,415 watts per square meter. Not a bad amount of light. That's pretty intense, actually. That's really intense, actually. That's a fair amount of light. Now, there are other things that actually impact this. If we were to look at this in a real picture, like 30% of this outright gets reflected back off into space, just off of our clouds and other things like that. There's a lot of different details, but that's nerd stuff, right? Let's focus in on the important things here. The dollar bills. How much money is the sun throwing at the Earth every single day? If we covered the entire Earth in solar panels, got rid of all the clouds, got rid of all the atmosphere, all those things getting in the way of that precious sunlight, how much energy, how much money could we be getting from that amount of energy? Now, this is where one more value is going to come in. I'm going to say this is dollar per energy is what we can call this. This is going to be a strange one. Dollar per energy is equal to, and this is a strange unit, not a unit we have seen, 1 kilowatt hour. So 10 cents per 1 kilowatt hour. Is this actually, it's a dollar? How did I do these units? Let's, I think I screwed these units up a little bit. Let's write it like this. $0.1 is equal to 1 kilowatt hour. It is an energy quantity right there because it is realistically kilowatts times hours. That's not joules, but we can turn it into joules. Here's what we need to do. We need to take this 1 kilowatt hour. We need to say, okay, first I'm going to convert that kilowatts back into watts. So there are 1,000 watts per 1 single kilowatt. And there are 3,600 seconds per 1 hour. Watts times seconds gets us right back into joules, our favorite unit to work in at all times. And do I have this conversion here somewhere? This should be something like 3.6 times 10 to the 6th joules. So that's our value right there, right? 3.6 times 10 to the 6th joules, that's equal to 10 cents. $0.1. Or, take this a little bit further, we're looking for essentially dollars per joule. Here's how we can do this. Take our 0.1, divide it by our 3.6, just call it megajoules. We're getting a quantity something like this. 2.778 times 10 to the negative 8th dollars per joule. And this is not anything to do with space or anything else like that yet, right? This is quite literally, this is what your energy company charges you. Per joule, really not too expensive. And this is on the high end of prices. You can shop for lower prices than this. Anyways, we've got that quantity in our back pocket now. The real trick now is to figure out how much of this energy are we actually collecting? Because this is how much money it would be per energy, but we need to know what is the energy in the first place. What does the Earth look like from the sun's perspective? How much energy, how much of that space are we actually taking up? And let's think about it like this. If you cover up one eye, you look at the sun. Don't look at the sun. Look at the moon. You cover up one eye, you look at the moon. What do you see? What do you see up in the sky? What does the moon appear to be? What shape is it? A circle. Exactly. Don't anybody tell me it looks like a sphere. You don't know that it's a sphere, right? Realistically, you can't see the depth of that object. And realistically, we know it's a sphere. Of course, it's a sphere. We have done this. We have known this for a very long amount of time, all of that good stuff. I'm not going to get into any of those details, Flat Earth Society or anything else like that. But when we're looking at it from our perspective, if we're imagining the whole of the sky is a big sphere all the way around us, how much of the moon, what portion of that is the moon taking up? The moon appears as a circle cut out of our big sphere. So too, if I'm standing on the sun, I'm Smash Mouth in early 2000s. If I am standing on the sun and I'm looking out at Earth, what do I see? A tiny little circle. Early Smash Mouth is fantastic, by the way. I'll stand by that statement. We used to blast that in the lab sometimes. So here's what we're trying to imagine, right? We have essentially the sun. What is that thing doing? I'm going to draw this small so that I can draw this large enough on the outside. It is going to be emitting all of this light in a really big circle that's supposed to look something like this. So this is like, I'm drawing this as a dotted line to say, hey, this is like the sun's intensity, the sun's light, escaping out in a big circle like this. With all of these arrows, it's going outwards. Outwards and outwards and outwards and outwards and outwards. The Earth is a pinhole in that. The sun at the equator is not the same as the sun at the North Pole. Very little light reaches the North Pole because what's going on there, we have the difference in what we call insolation. And not insolation, insolation. Solar kind of sound on that one. What's going on with that one is that because of the angle of this, the same amount of light that would be hitting that is spread over a much larger area. So the fact that the Earth is actually a sphere doesn't really actually account for how much of this energy we're taking. We are effectively a circular pinhole in the big spherical wave that is the sun's light. Here's Earth. A pinhole. How much of a pinhole? Easy. Take the Earth's radius. That radius being 6.37 times 10 to the 6th. We are the area of a circle collecting that sun's light. We already know what the intensity looks like out here. So let's say that the power should be the intensity times the area that it's hitting. We've already got the number for intensity, so I'm just going to plug in. We've got pi r squared. Plug in those quantities right there. What you should find is a power something like 1.8 times 10 to the negative 17th, or positive 17th. 1.8 times 10 to the positive 17th watts. I want to know how much energy do we get in a full day. So I take this power, multiply it by 1 day. That is 60 seconds, 60 minutes, 24 hours. At the end of the day, we get 1.56 times 10 to the 22nd joules every single day. 1.56 times 10 to the 22nd times our value for the dollar per joule. Dollars, money, is equal to $432 trillion worth of energy every single day. Cover Utah and solar panels. We could debate the state a little bit, but I'm not completely against it. How do we feel about this one? Any questions or any details that I can clarify a little bit better? This is a little bit different, right? I realize that this is a little bit different, but this is maybe a little bit closer to a lot of the problems that you'll actually be facing out there, right? We take some of these equations that are definitely just physics-based, and we combine them in the sense of, okay, what's something like a cost analysis or details like that, where you're really coming up with the equations on the spot. You're figuring out how these things have relationships together to come up with some reasonable number for what you're looking at. Physics is a tool, right? I know that you guys are not all, a handful of you, are continuing to study physics specifically, but for most of you, physics is going to be one of those tools in your tool belt that you carry with you going forward. All of these equations, all of these concepts are things that you use, not necessarily things that you focus in on, but they are useful tools in your future endeavors. Now, we're not going to have time to cover all of this stuff right now. And that's all right, because if you notice, if you have already looked ahead at the 17-1, this is a common theme. We either make it all the way through these slides or we get stuck halfway through, so I'm not worried about it. I've already got that planned in for the schedule and everything else. But while I've got a little bit of time left, let me just begin to talk about some of these things, because they are pretty important conceptually. You know what the Doppler effect is. Realistically, you have heard it before in your life. This is not anything new, at least if you have not studied it with equations. You have certainly heard it in some sort of context. Think about the difference of sound when the train runs through Oxford. You hear that horn differently depending on where it's at. And the big reason for that, what makes the Doppler effect work in the way that it does, is the fact that these are a bunch of series of compressions. There's a certain speed that waves are going to travel at through air in the first place. If the source of that sound is also moving forward, once it is emanated from the object, it doesn't have any additional, like the sound does not have an extra forward velocity once it has left. The speed of the wave is determined by the medium, not the object that was generating. So as soon as the object leaves this forward-moving object, now it's traveling at a straight 343 meters per second. That's it. That means that if something is constantly emitting sound as it's moving forward, then it's smashing those compressions together, compressing the compressions, if you will. And by compressing the compressions, we shorten that wavelength, we ramp up that frequency, we hear a higher pitch. Think about what happens when you hear sirens passing by. When the sirens are coming closer to you, you hear the sound of wah, and it's not something that is going on with the siren itself. I know the sirens do increase in the pitch, but you can hear this very, very stark difference. As it's coming close to you, you hear the wah, and then it sharply stops. As it passes you, it goes back to the wah kind of sound. The middle goes up, straight from the middle, and then it drops all the way down. Wah, as it goes farther away. Because once you're moving away, you're doing the exact same thing, but in reverse. The wave speed is still going to be the same. But now where those compressions are generated in the first place are further and further away. So the Doppler effect depends on whether the object is coming towards you or away from you. If it's moving to the side of you or anything else like that, you are not going to notice the Doppler effect. It will not change the pitch. It doesn't change the rate at which you receive these. But if it is moving towards you or away from you, you will hear a difference in pitch. And my task for you, until we see each other again, is going to be to listen for these things. If you're in Oxford, there are sirens constantly, or there are trains constantly. There are all sorts of random things. You will hear this. People that have seemingly removed the muffler from their car. You will hear all sorts of loud sounds that are moving at fast speeds. And I want you to be listening for those things. Hear what they sound like. Do they change the pitch? Do they stay the same pitch? How are they moving relative to you? And how do you hear that sound as they move? That's your task. Bring this in with some real-world experience here, because I promise this shows up all over the place, right? This is not a crazy new thing or anything else. It's quite a fun thing. So next time we will get a little bit more into these equations to describe it in a little bit more detail, but that is already planned out. I've got that set up in the slides already. Go ahead and just think about this stuff. Look around you, listen around you, find all those details out in the real world, because they exist out there. No in-class for the day. Some reading questions, though. We'll have another in-class on Wednesday, but it's going to be through Mastering. If you want to get an early look at that, you're more than welcome to. Good question. Fundamental frequencies, standing waves, acoustics, beats, interference, mathematics. I don't think there are. Oh, I'm looking at not even the right section. Never mind. Hang on. There might be. Let me make sure there's not. There is one. Maybe two. Maybe a handful of these. Okay, here's what I'm gonna do. Okay, good point. I'm not gonna change anything about that. I'm just gonna let's push back the homework from today's lecture by a couple days, just to make sure that we've got time to cover it. Just to make sure we got time to cover it. That way we'll be all taken care of. But go ahead and take a look at it ahead of time because, you should be able to get at least partway through this, and then we'll talk about it in a little bit more detail next time around. Sound good? So, thank you guys for being here. I always appreciate it. Have a fantastic one. I'll see you guys again next time.